Let's resume. We talked about the trigonometric functions of arbitrary angles, but we weren't able to discuss one very important application in geometry. It's this one. The area formula for a triangle when two sides and an angle between are given. I hope everybody remembers the area formula of a triangle. A is 1/2 A times h, where A is the base length and h is the height. What if h is not given? Instead, we have two sides A and B and the angle between. Kind of like this. This program is, by the way, randomized, so each time I run, I'm going to get different triangle. In this case, we got an obtuse triangle. Well, in this case, we got a acute triangle. So acute case is a little bit easier to understand, so let's go over this first. And okay, the area formula is 1/2 AH. But we can find out what h is using a trigonometry. Here's a proof. A is 1/2 AH, and h happens to be b sine of theta. Why? Well, let's see. I'd like to see this picture and the proof in the same viewing window. It's a bit too difficult to do that because this picture is too tall. Okay, I like it better this time. Okay, and where were we? Yes, from the trigonometry, b is hypotenuse. So h over b is opposite over hypotenuse, so that's sine of theta. So h can be written as b sine of theta. So substituting h equals to b sine of theta in place of the area formula, a equals 1/2 AH, we get the desired formula, 1/2 AB sine of theta. What if we have an obtuse triangle, by the way? No. Okay, kind of like this. I'd like to see it in the same viewing window. Okay, this picture is good. What if we have an obtuse triangle like that? In that case, again the same thing because h is vertical. And b can be understood as a radius if you consider the center point as the origin. So the same identity, h of b is sine of theta, stays the same even when theta is obtuse. So what do you get? H is equal to b sine of theta. Substituting h equals b sine of theta into the original area formula, 1/2 AH, we're going to get the desired formula. A is 1/2 AB sine of theta. Okay, we proved it. So let's do a couple of exercises. How about something like that? Find the area of the highlighted region. Well, what's the strategy? I'd like to use this strategy. Let's see. Okay, find out the area of the sector first, and then subtract away the area of the triangle. Excuse me, where's the command? Okay, let's look at the first graph. This is what we want, and this can be obtained by calculating the area of the sector first, and then subtract away the area of the triangle. Then what's left will be the desired region here. So how do I set up? The area formula of the sector is 1/2 r squared theta. And the area formula of a triangle is 1/2 r squared sine of theta. Because Well, A and B are equal to R in this case because we have an isosceles triangle given by the radius. And plugging in all these values, theta is equal to what? 2 pi over 3 in this case, and the radius R is 4. And calculating out, we get this precise answer, 16 pi over 3 minus 4 square root of 3. And further computation yields this numerical value, which is an approximate value, 9.82 something. How about something like this? We have a sector and a triangle, but how do we handle that? Well, let me give you just a hint. Okay, let's compare these two pictures. This first picture, everything is shaded, and in the second picture, the sector is shaded in light red, and the triangle is shaded in light blue. So what you need to do probably will be, okay, I'll stop here. How do you figure out the area of the shaded region, highlight region for this? From this picture. Okay, I'll stop here. I'll let you figure this one out. And then let's move on to the graphs of trigonometric function in the next video.